Hi, in this presentation we're going to talk about principal component regression. So what does this mean? This looks similar to something you've seen in class, namely principal component analysis. So first of all, what was principal component analysis? You learned about principal component analysis, or PCA, as a dimensionality reduction technique. Namely, if you have a bunch of data points, I collect them into a matrix X. Let's say you have data points x1 up to xn in p dimensions, so that at the end of the day I get an n by p matrix. And let's just to keep in line with class and to make it a little bit simpler, let's assume that my data is centered. That is, that the empirical mean of all my data vectors xi is 0. So if I have this, then one question you could ask is, if p is very large, how can I get a good reduction of the dimensionality in all my data points? For example, why would you want to do this? Maybe you want to plot all your data points. And if p is 10,000, then it's not so clear what you should plot. Should you plot just some two random directions of your data points? Or should you do something different? And the answer that PCA gives in this example is the following. You form the empirical covariance matrix of your data points, which is 1 over n x transpose x. And for the sake of this recitation, let's just assume that we're not normalizing by n because we won't actually need it. So then what you do is you compute the eigenvalue decomposition of this symmetric matrix. We know from linear algebra that it exists. And it will look something like this. P d p transpose, where P is an orthogonal matrix. That means P transpose P is the identity in p dimensions. This is a p-dimensional matrix. What this means, in other words, is that the columns of P, which I'll denote by V1 up to Vp, are orthogonal vectors and that they have unit norm. Moreover, there's this matrix D. D is a diagonal matrix. And let's call its entries lambda1 up to lambda p. And the rest is 0. And all these lambda I are larger or equal than 0 because this matrix is positive semi-definite, because it is a product of two matrices like this, x transpose times x. All right. So what does PCA do? PCA says, well, take this matrix and just look at the largest values. Actually, I want also that lambda 1 is the largest and lambda p is the smallest. So take the k largest of the lambda I, and then project to their associated eigenspace. That is, we introduce a reduced matrix, pk, which just consists of the first k vectors of the original p. And then we can project our data down, because this x contains the data points transposed. What this looks like is that you'll have a new matrix Z, which is x pk, or in other words, you have data points zi. These are the rows of Z transposed that are pk transpose multiplied by a xi. That is, you take each of your data points and you project it down to a k-dimensional space. For example, if you want to plot something, you would take k equals to 2, and you would get a projection to a 2-dimensional space, which is good for visualizing things. So what this does, what this eigenvalue decomposition does, is it picks the directions with the biggest variance. What does that mean? let me explain it by a picture. So your data might look something like this, like the picture, like a plot on the left. So here I've just drawn some points following a Gaussian, a multivariate Gaussian distribution, which has much higher variance in the diagonal direction 1, 1 than it has anywhere else, or than it has on the skew diagonal 1, minus 1. So if your data looks like this, you see that there is much more variation among your points in this diagonal direction, in this direction, than there is on the off-diagonal direction. So why not just project down to this direction and retain most of the variance of your points? And this is what I plotted on the right. This is what happens if you look at the if you look at the covariance matrix of your points and you project down to the leading eigenvector. And now I pulled the points back into their ambient space. So in some sense, what I did is consider x, pk, pk transpose here. So you see basically what happens where that first direction lies in space. But I could just as well basically plot this as a one-dimensional just a one-dimensional plot instead of a two-dimensional plot and retain all my points. All right. So why would we do this exactly? Because we need to plot our data, and because retaining the variance is one natural criterion which we could follow to choose our directions. It's not the only one, right? So you could think of others, but it's a somewhat natural one, and it aligns very well with linear algebra. So computing this eigenvalue decomposition is something we can do in practice. OK, so what's the relationship to linear regression? So let me first write down our standard linear regression setup, where we observe samples y as a linear transformation of some data, and I'm using the same notation x for our data, plus some Gaussian noise epsilon. And for simplicity, let's say that epsilon has covariance matrix identity in n dimensions without any sigma squared or something for scaling here. OK, so y is supposed to be n-dimensional, x is n times p-dimensional, beta is some p-dimensional vector, and epsilon is noise, and it's n-dimensional. Now, you've learned how to solve this, or you've learned one estimator you could think about here, namely the least squares estimator, or ordinary least squares estimator, which I'm going to denote by beta hat OLS, which is the minimizer of y minus x transpose beta Euclidean norm squared, or alternatively can be written as x transpose x inverse x transpose y. Now, what's the problem with this? One of the problems is that there is a matrix inversion here, x transpose x inverse. And this matrix might not in all cases be invertible. This is especially true if p is larger than n, then there is no way that this matrix is actually invertible. And actually, you can think about it, there is no way that there's a unique minimizer of this objective. So when does this happen? Usually that doesn't happen, right? If you have a 2D setup and you just want to fit a line to some points, there should always be enough data points. There should always be at least 2 data points, right? But sometimes we're using linear regression for more complicated things. One example is GWAS studies, genome-wide association studies, where we're trying to find relationships between certain genomic markers and certain traits or diseases. And in that case, our number of covariates, those genomic positions, might range in the millions, or might be more than a million, while the number of data points might be a couple of thousand. So in that case, we clearly cannot use something like ordinary least squares. And the idea here is the following. Why don't we just reduce the dimensionality first? Then we get new points in new coordinates, and fewer of those, and regress onto those reduced coordinates, and then pull it back to see how well certain linear combinations of our points actually influence the outcome, the y's. In other words, let me write this down. So this is going to be principal component regression. So first, perform PCA in your data and pick a k. And we can talk a little bit about how to choose k later. And then do the following. We are going to compute a gamma hat, which is trying to explain our outcomes y, again, via linear regression. By regressing onto our projected data. Now, notice this is not going to be p-dimensional. This is going to be a k-dimensional vector. And then we are going to pull back our data and set the PCR, principal component regression estimator, to be the projection of gamma back to the original space. That is, it's going to be pk gamma hat. OK, so let me write down the same formula that applies to the ordinary least squares estimator here. So this is just another matrix, so I can use exactly the same formula. Namely, I'll have this matrix transpose itself. So x, first transpose. So pk transpose, x transpose, and then the same matrix without the transpose. Inverse, and then x transpose, that is pk transpose, x transpose y. And I can plug in the same calculation here. And it's going to be pk transpose, x transpose, x pk, inverse pk transpose, x transpose y. So now, look at the matrix I'm inverting here. So this is taking the original matrix and then projecting it down to a much smaller space, inverting it there, and then pulling it back, basically, projecting it back to the original space with pk and pk transpose. So now I have a much better chance of actually inverting the matrix and getting an estimator. But of course, I'm paying a price. And this recitation is about trying to formalize, at least in one sense, what the price of doing this is. In other words, I'm going to be interested in the risk of both the ordinary least squares estimator and the principal component estimator, regression estimator. And so in order to tackle this, we'll first talk a little bit about risk of estimators. Then we'll look at the distribution of beta hat PCR. And then we'll make a little table, I'll do that afterwards, about certain components of the risk of both the PCR estimator and the ordinary least squares estimator. And if we have time, we might also talk a little bit about the ridge regression estimator, which you've seen earlier, which fits actually into a similar framework as the principal component regression estimator. Now, one more thing, how to choose k. We'll see what actually an optimal choice of k could look like, but it does involve knowledge of the underlying beta, which is unknown. So what we do in practice most often is to have a look at the variances here, and this is called a scree plot. And it might look a little bit like this, where this is the first. So here are the values of the lambda i's, and here is the I. So that means your biggest eigenvalue might look like this, second biggest like that, and so on. And we're basically looking for an elbow like this. So for a sudden inflection point like this. This is usually when we postulate, or we think that there is essentially the inflection point happening from actual data to mostly noise. But you can think about other criteria that involve how much of the variance that you see in your data points is explained. And Philippe talked a little bit about those. OK, so one more thing about this PCR estimator. You should be aware that what it does is kind of explain everything in terms of linear combinations of your data. You can later pull it back and actually obtain an estimator for beta here. But it essentially factorizes through this gamma hat. And that means whenever things are indistinguishable in your projection, then they will also be indistinguishable, and they will not be correctly picked up by this PCR estimator. Let's go back to the plots I showed you. If your data actually looks like the plot on the right, so this one here, then it is not possible for you to actually distinguish the effects of either of the variables that are governed by the axes, right? Because you'll never see variation along this direction. The only variation you see is how well do they vary together. Think about running a regression, for example, for the following problem. You want to find out how well people are doing on a statistics aptitude test given their IQ and their income. And if the IQ-income distribution looks a little bit like the thing on the right, then you'll be hard-pressed to actually distinguish between any relationship given by IQ or income separately, because they always vary together. And what PCR says is it's trying to be honest to that fact and essentially just treat income and IQ as one variable instead of two, because in your data it actually looks like they are maybe close to only being one variable. And then it'll tell you, well, the outcome of the statistics aptitude test might correlate positively with a joint covariate, and this is described by this gamma hat, with a joint covariate given by linear combination of IQ and income, but you will not be able to tell anything about how well either of those separately correlates compared to the other. All right, so why don't you first, while I'm erasing, calculate an example of this estimator in a two-dimensional case. And when we're back, I'll talk a little bit about the risk of estimators.